The quantum mechanical model of the atom. We're going to understand this little graphic right here. You know, you're going to look at that and go, oh, I understand. That's a nucleus. And I see the 1s shell, the 2s, or excuse me, the 1s orbital, the 2s orbital, the 2p orbitals. They're all right there, right? And this is some of the stuff from the quantum mechanical model that we saw in Crash Course Chemistry, kind of looking ahead. And I said, don't worry, it'll make sense to you. Eventually, when we get there, you just have to be exposed to it a little bit more. So real quickly, looking at the history of the atomic model, the atomic theory. We've already talked about Dalton. You remember Dalton's concept was that matter is these small individual pieces called atoms, non-destructible pieces. And so kind of like the image of matter from the philosophers, it was little balls of matter that came together and interacted and were indivisible. But Thomson came along. Remember what his model was called? Known primarily as the plum pudding, right? We'd call it maybe the English, or that's the English version. We'd call it something like the blueberry muffin model or maybe the chocolate chip cookie model. Makes more sense to us. But that the whole atom was positive and there are little pieces, little nuggets of goodness called negative charges in the middle of the big positive. And then go on to Rutherford's model. Rutherford said, you know what? That positive goodness is not spread all over the place. The positive goodness is all put in the nucleus. And so Rutherford's contribution, yes, was the discovery of the proton, but more significantly than that, in your review question, was the nuclear model, that the positive charges were all in the center. Okay? So yes, protons came out of that, but protons saying, they're all concentrated. It's not all big positive goo. Positive pieces are in the middle, and electrons exist outside of that middle, separated with mostly nothing. Empty space with electrons. And then Bohr came along. We just finished with Bohr. Bohr is not boring, right? Bohr said, okay, we've got positives, and by then neutrons have come along as well. So positives and neutrals are in the nucleus, and they're surrounded by these electrons. And whereas we may have had a planetary model, kind of Rutherford saying, you know, all of these electrons are circling the nucleus kind of on a racetrack. Bohr comes along and says, wait a minute, they're not all on the same racetrack. There are varying levels of energy. And that the lower energy level is closer to the nucleus, and as we go away from the nucleus, we go to a higher and higher energy level. Because remember, the energy would come in, excite the electron, it would go out to a higher energy level, farther away, and then we visualize that as, okay, after it's there for a moment, it wants to go back to a ground state, it falls back down, emits energy, because it has to get rid of the energy to fall. And when it emits that energy, we see it as a photon of color, and it's dropping between distinct steps, distinct energy levels. So that's what Bohr is talking about. And we said, okay, all of this is important because we're going to use all of this when we visualize the modern theory, the quantum mechanical model. But the quantum mechanical model is something different. The quantum mechanical model talks about not orbits, like distinct levels, but orbitals. And an orbital, we're going to visualize this in a way, but an orbital is basically not exactly where the electron is, but the probability that the electron is there. Because electrons get kind of weird and funky with quantum physics on whether or not an electron is actually a particle that's in a place or it's the result of an intersection of waves and it has a multiple location duality kind of beyond our ability to completely articulate kind of thing. So we're going to be talking about electrons as if they're particles, but I want you to always keep in the background, ultimately the quantum mechanical model doesn't treat the electron as a particle, it treats it as the result of the intersection of waves. Okay? But most of my presentation is going to be based on assuming it's a particle because it helps us make sense of the images we're going to see. So like we said before, models aren't designed necessarily to present reality as much as models are occasionally used to help us understand. They're like a metaphor. Okay, in this case, we're going to use a metaphor of particularity of a particle, and we talk about where it could be, but we can't know exactly where it is. Again, hopefully it'll make more sense, and if you're into that kind of fuzzy logic thinking, you know, non-particulars. There's a lot of that kind of thinking going on with what we're going to be talking about right now. Anyhow, let's go ahead and move on. We're going to talk about these orbitals, and unlike the orbitals in the Bohr model, if you think of the Bohr model, it's basically sequential circles, racetracks, if you will, level, 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 and everything's dropping nicely between one level and another level and emitting a photon. When we get into the quantum mechanical model, there are 4 different kinds of orbitals we're going to be talking about. And again, the thinking is, for these different orbitals, the Bohr model fits really nice in a 2-dimensional plane, right? If I draw it on the board, it's nice and flat, like an old-fashioned record. Maybe that's before your time. An old-fashioned CD. That might be before your time, too. Okay, but anyway, so it's this flat surface disk with different racetracks around it. Now we're going into the orbitals, and we're starting to say, hey, this is more like real life. This isn't 2-dimensional. This is 3-dimensional space. What we're trying to draw on the board are things that have height and width and depth. So it gets complicated at times because we're showing 3-dimensional things on a 2-dimensional plane, which is why later on when we do molecules and the molecular geometries and things like that, we'll pull out the little models, the little stick models and little balls, and we'll like look at it in 3 dimensions, and we'll try to draw it in 2 dimensions. And then we'll try to draw it in 3 dimensions in a way that makes sense to our eye that, hey, there's depth there. It's like going to 2-dimensional art and then taking it to 3-dimensional art and having vanishing points and all that kind of stuff. We use little symbols in here to help us see it. Oh, that's a 3-dimensional view, not a 2-dimensional view. So anyway, these different orbitals, they represent places where the electron will be, where it will probably be. Different regions have higher probabilities. But if right now you want to think of it, rather than saying, okay, here is a racetrack in a 2-dimensional space, you can think of it as a sphere, and it is a sphere, in a 3-dimensional space. Oh, but the electron isn't necessarily right on the surface. It's at or inside the surface of the shape. So the electron doesn't have to be here, 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 or on the surface here, on the back there. It could be inside the sphere. If this is a ball, you can think of the electron as a BB inside of the basketball. Where's it at? Don't really know, but it's in there. Okay? So these different shapes, these different orbitals, we're going to walk through each one of them and describe them. One thing I'd like you to understand, though, is that every orbital can only contain 2 electrons. So it'll make more sense because ultimately what we're driving towards is how do we build a configuration for an atom that has, let's say, rubidium has 37 electrons. What does its orbitals, what do they look like? Where are these 37 electrons at? Now, if it was the old-fashioned simple heliocentric model, we draw one circle around the nucleus and put 37 electrons. And that's not the way it works. Oh, if we did the Bohr model, we would have a nucleus and we'd have concentric circles and we'd add 37 total between all the tracks. Closer, but that's not really how it works. It looks more like this confusing 3-dimensional cloud probability structure. So, one way that they say in the book to think of it, may be helpful, is in the Bohr model, if you think of the electron as being like a dog on a chain or a dog on a rope, okay? If that dog is always pulling to get away from the center, he's always going to be that same distance, whatever length the rope is, and is going to scribe a circle in your lawn, aren't they? There's going to be this bare spot where the dog goes around this pole, and if it's not like brings him in and ties him to the pole because he goes around it, let's say it slips. So he has a certain distance from the pole that he can be, and he's always that distance from the pole. He's going around and he's wearing out the grass in a circle. That's a Bohr model understanding of electron. The quantum mechanical model of the electron has that dog not intent on just simply being as far away as it wants to be, but it can be anywhere between the pole and that point. It can move inside the circle and move around inside the circle. It doesn't have to be just simply as far away from the pole as it can be. Does that help? Make sense? So in that model, the electron is like the dog, and it goes around the pole, but it's not always pulling on the chain to get as far away as it can. Sometimes it's walking through the middle, sometimes it's just laying down, sometimes it's moving around, but it's not always as far away as it can get. These different shapes, S, P, we also have Ds and Fs, different kinds of orbitals. We're going to talk about 3 of them and only kind of try to draw 2 of them because they get pretty crazy. Hard to visualize, hard to draw, Usually the D's, and especially the F's, are only really done by computers. People don't tend to sit down and draw the F orbitals. It's too strange. So here we go. Let's go ahead and kick it off. The s orbital. It's the most basic orbital shape that we have. Matter of fact, it's the first orbital that gets filled. The s orbitals, right now, we'll just think all s orbitals are spheres. And I wrote down for the s, it's a simple sphere, and it's centered on the nucleus. So the s orbitals are simple spheres. Again, think of it like a ball, a beach ball. At the very center of the first s orbital, and actually, technically, in the center of every orbital shape we're going to do is the nucleus. Everything centers on the nucleus. So the first shape, this s orbital, at the very center of the s orbital is the nucleus. And so the s orbital represents a ball in which electrons can move, up to 2 of them, right? Up to 2 of them can move within that ball, and in the very center of that ball, suspended exactly in the center, is the nucleus with all the protons and all the neutrons. Okay? Now, it would be easy if there was just one s orbital, and there are more s's. But the nice thing of them is that they're all concentric circles. There's a 1s, and that 1s represents the first energy level. Let's think of it like this. In the Bohr model, remember we had the rings? There was one energy level, then there was a second energy level, and there was a third energy level. Think of the s orbitals, if you look at them in 2 dimension, as balls that contain that entire orbital space. So we have a 1s orbital. It's a nucleus right in the middle. This is our 1s orbital. We take it up to the next energy level. Boom, okay? Now we're at the second energy level. Guess what we find at the second energy level? The 2s orbital. The 2s orbital is a larger ball, and inside of that is the 1s orbital. And inside of that is the nucleus. So you see that this larger second 2s orbital has within it the 1s orbital, which has within it the nucleus. And that's what we're going to do. When we talk about the s orbitals, it's going to be the nucleus, the first s, the second s, the third s, the fourth s, the fifth s. Those spherical orbitals are going to grow, and each higher energy level represents a larger sphere that contains all of the lower level spheres. It's like those little Russian dolls, right? You take one, oh, there's a littler one. Take it off, oh, there's another one in there. Take that, there's another one in there. So if we were just simply looking at the s orbitals, we'd have a large ball. We'd open it up, and in the middle of it, perfectly in the middle of it, would be another ball. Open that up, perfectly in the middle of that is another ball. Open that up until we get all the way down to the 1s. Open that up, and perfectly suspended in the middle would be the nucleus. Okay? Let me see if anything else. Nope. Simple spherical centered on nucleus. Energy levels expanding. So as we go from one energy level to another, and I know that's kind of a term right now, energy level. Just think of it as the Bohr model, from one place to another place, from which it would fall to give off energy. See, remember, it's going to be either in this ring. In the Bohr model, it's either going to be in this ring, it's going to be in this ring, it's going to be in this ring. In the quantum mechanical model, it's either going to be in this sphere, or the larger sphere that contains that, or the larger sphere that contains that, and so on, all the way out. So the larger the sphere, the higher the energy level. The smaller the sphere, the lower the energy level. Every sphere can contain 2 electrons. Okay, that's the other important part. And again, original thinking was that, hey, this must be the way, if you think of the Bohr model with multiple rings and multiple electrons on it, it kind of looks like this, doesn't it? In 2 dimensions, it looks like a Bohr model. But in the quantum mechanical, remember, the electron doesn't have to be on the edge. It can be anywhere inside that circle. And on this one, oh, by the way, it can be anywhere inside the circle. And in the third energy level, it can be anywhere inside that circle. Right? But not all of our orbitals are nice, perfect spheres like this. The second orbital we're going to discuss are the p orbitals. Now, in the first energy level, The only orbital we have is the s orbital. When we move out to the second energy level, now we add the p orbital. So we have a 1s orbital, we also have a 2s orbital, and then we have a 2p orbital, or actually 2p orbitals. There are 3 of them. 3 p orbitals, and they're all oriented, if you look at a graph, on the axis. So there's a vertical, a horizontal, and an in and out. And these shapes all come together to form, when they're all formed, a shape that looks like this. You can think of them as figure 8s. I sometimes refer to them as dumbbells, right? You know, one-handed dumbbells. They look in that way. So every one of these can contain 2 electrons. And they're oriented in the 3 different dimensions. So there are 3 orbitals. Each can contain 2 electrons, which means the p orbitals for every energy level can contain 6 electrons, right? I can put 2 electrons in every s. I can put 2 electrons in every p. Oh, by the way, when I get to 1s, there's only 1 orbital. 2s, it's 1 orbital. 2p, I now have 3 orbitals for 6 electrons. These dumbbell shapes are centered on, you guessed it, the nucleus. The nucleus is always going to be the center of every one of these orbitals. So, again, going back to the concept of energy level, I've got the 1s, which can contain 2 electrons. The next shape I have is the 2s, that can contain 2 electrons. Then I have the 2p orbitals, which can contain 6 electrons. Then I move up to the 3rd energy level. Guess what the first shape we're going to talk about from the 3rd energy level is? It's the s. Every energy level contains the s orbital. Starting at the 2nd energy level, it includes the p orbitals. And then moving up to the 3rd energy level, we start talking about the d orbitals. You're not going to have to draw these. You're going to be drawing s's and p's, but don't worry about drawing d's. There are 5 orbitals in the d's. Each orbital can contain 2 electrons, so for a total of 10. Okay? So we've got the s's, which are spheres. They're at every energy level. P's, which contain 6, and they start at the 2nd energy level onward. D's, which contain 10, and they start at the 3rd energy level and go forward from there. 5 orbitals, 2 electrons per orbital, for a total of 10 electrons that can live in the d orbitals at any given energy level. Confusing yet? Okay, just general bobble. Getting it kinda? We're gonna apply it in a minute. But I just want you to get this general feel for, hey, look at that. Does this picture now make a little more sense to you? Do you see the nucleus? Do you see that every shape that's around that nucleus is centered on the nucleus? Do you see that there's a spherical shape indicated on the inside there? What do you suspect that is? The 1s orbital, which contains 2 electrons. And then we have another concentric circle. What do you suppose that 2nd circle is? It's actually a sphere. It's the 2s orbital, and it has 2 electrons in it. And then within that, we have these lobe kind of things that are coming from the center out. What do you suppose those are trying to represent? The 2p orbitals. Okay? See how they're all centered on the nucleus. See how they form, the s's particularly, can form concentric levels that enclose the lower levels. Notice how we've got the p orbitals all stuck to the center, all rooted in the center and offset in different coordinal directions. That's what you really need to pick up for now, just that idea. Because a lot of what we're going to do is very practical application of this on saying, okay, I've got a certain atom, what does its electron configuration look like? And that's what we're going to try to push into in just a moment. We're going to back up just for a moment as well and talk about this. We mentioned it the other day, this idea of ground state and energy level. We said that all matter tries to stay in the lowest possible energy state. And this is one of those times that we're going to do quite often in chemistry, is we're going to kind of anthropomorphize, or we're going to imply like a human characteristic. I would argue that matter has no emotion. A matter doesn't care. So how can it try? Why does it try? And I would argue that it's not based upon the matter. I mean, the electron's not going, dude, I'm all energized. I need to get rid of this extra energy and fall back to a lower energy state. There's not a reasoning taking place, but rather it's part of the laws of nature, laws of God, his character, that says energy is going to be at its lowest state. And occasionally it's going to get zapped and pushed up, but you know what? It's going to return to its ground state. And the ground state is the lowest possible, the lowest possible energy state for any given substance. Energy wants to find its way back to ground state. Think of it this way. Why does all water flow to the ocean? Because if it's higher than sea level, it's trying to find a way to get lower. And if it's stuck in a pond or something, it may not be able to do that. But if it's in a stream, it's going to rush to sea level. If it finds a place that's lower than sea level, guess what? It's going to stay there. We don't find many rivers that go down the hill and up the other one, do we? It's trying to find its lowest possible energy state. Why do we ground our houses for electricity? Because electricity seeks the ground state. It wants to be grounded. We do it for protection for ourselves and also to define voltage based upon an absolute zero, that grounding state. And so ground state is just one of those things in science where we say matter seeks the ground state. Why? It does. There are maybe technical and scientific reasons for it, but right now for this course, because it does. And that's good enough. Why does that excited electron, de-excited, emit a photon? Because it wants to be at ground state. Why? Because all matter wants to be at ground state. Why? Because God said that's the way it's going to work. Again, there may be scientists who push back against the God concept and say, well, here's a scientific reason why. I would argue that's embedded in the whole, thus saith the Lord. Okay? So we're going to look now to the Bohr model to help us understand how to build up electron configuration. Here's the deal. I'm going to ask you in a minute how to write the electron configuration of an atom from the periodic table. And there's a certain way we can do that. One way is the way that I learned when I was in school back in, say I took chemistry back in 1981, 1980. Okay, I took it again in college, but I first learned the slant table back in the early 80s, late 70s. What I'm going to do right now is have the PowerPoint show you the different configurations, the different orbitals. We have, in the first energy level, just the s orbital. So we have a 1s2 configuration in the first orbital.
I'm sorry, they're ready for the juniors.
So we're going to build up the electron configuration, and what we're going to do on this diagram is I'm going to show you both the orbitals that are in each energy level and then the order in which they're filled, because frankly, even though they list out in order, they don't fill in order. It's a little more complicated than that. So there are two ways of determining the electron configuration for any atom. One of them is using the slant table, and this is the way I learned it. So in the first energy level, that first number represents the energy level. The second indicates the orbital shape. And the number in superscript is the number of electrons that are in that orbital. So for the slant table, it's going to show the maximum. How many can the s orbital hold? It can hold 2. How many orbitals are in the first energy level? Just the s orbital. Just the 1s orbital is the only first energy level orbital. Second energy level, the 2 energy level, the second, has a 2s orbital and has 3 p orbitals. We don't say px, py, pz. We just p6. So 2s2, 2p6. Do you see that that represents the location for 8 electrons? 6 in the p orbitals, 2 in the s orbital. Now going to the third energy level. What do we anticipate seeing at the third energy level? 10. Okay, we're going to see the s, the p, and the d. So the third energy level has the s orbital, which can hold 2, 3 p orbitals, which can hold 6, and 5 d orbitals, which can hold 10. And we're just going to simply, in our configuration, know that as the 3s, 3p, and 3d orbitals. Fourth energy level. Same structure, 4s, 4p, 4d. Now we add the f orbitals, the 4f. F can hold up to 14 electrons. There are 7 orbitals that can hold 14 electrons total. That's as high as we're going to go. But for the purposes of the slant table, I need to show you that there is a fifth energy level, and there is a, we're just going to put the 6s. But there'd be a 6p, 6d, and 6f as well. All right? Now, here's the deal. Whenever we come up with a configuration for a particular atom, I need to know how many electrons are in that atom. How do I know how many electrons are in a given atom? How would I know that? If I say I'm doing calcium, how would I know how many electrons are in calcium? I saw one person gesture. Get a little more feedback than that. How would I know how many electrons are in any given atom? Go ahead. The atomic number. Because the number of electrons has to equal the number of protons, and the number of the protons is equal to the atomic number on the periodic table. So if I come over to calcium and say, I'm doing calcium. Calcium has an atomic number of 20, therefore calcium has 20 protons, therefore calcium has 20 electrons. I need to be able to count up to 20. I need places to put 20 electrons. Now, if it filled nice and straight, we would go, there's 2, 4, 10, 12, 18. I need 2 more for 20. Right? If the electron orbitals filled in order like that, but they don't. Always have to make it hard, right? So what they do for the slant diagram is, if you write this out, is they fill on the diagonal. They fill on the diagonal. They fill on the diagonal. On the diagonal. Now, up to this point, filling on the diagonal is exactly the same as filling in order. You see that? Because it's going to be the 1s, the 2s, the 2p, the 3s, the 3p. Oh, wait a minute. The 4s. The 4s orbital fills before the 3d orbital fills. And so on, and so on. So if I have an atom and I'm counting up to place all of its electrons, and let's say that it has, okay, if it's 2, it's here, 4, 10, 12, 18, 20, 30, 36, 38, 48. See that? You're going to fill in order of the slant diagram, not in order from left to right, top to bottom. Frankly, this was the only way I ever learned on how to fill the orbitals. But there's a much easier way. But this is one way, and actually, when we do a couple of the problems later on, I use the slant method and I use the second method. The second method is using your periodic table. This is much more obvious, much more graphical. So maybe that other way, for those of you who are coding, that's the code. Here's the nice graphical interface, looking at a periodic table. We mentioned before that the periodic table is laid out to communicate different pieces of information. And just like we said before, hey, why is hydrogen over here when it's a non-metal and it should be over there? Now we look on electron configuration, the exception is helium, and helium is over here because it's a non-metal, but for our purposes for this exercise, it should be over here. It should be on the left side, over here beside hydrogen. Because as you look at the periodic table, and you want to find out what is the valence shell, the valence, the most outside shell that's being filled, the most outside orbital, you can tell immediately from the periodic table what that will be. Because if the element resides in these two columns, its valence electron is filling an s orbital. And if the element resides over here, with the exception of helium, which should be over here, the valence, or the highest level electrons, are going into the p block, the p orbitals. Or if it lays out in here, we're filling the d's. And if it's down on this section here, we're filling the f's. Its last electrons are going to be going into those particular blocks. Okay? Okay, so the S's, the P's, the D's, and the F blocks. So notice from here that we've got the slant diagram. Notice that it goes, I mentioned before, that S's, P's, then the 4S fills before the 3D, then the 4P, then the 5S, then the 4D, like that. It kind of jumps all over the place. If we go to the periodic table, look what happens. If we bring this one to this side, we've got, now these are the energy levels. Your rows on the periodic table represent the energy levels. First, second, third, fourth, fifth, and so on. What energy level are we talking about? It's the row. Imagine that helium is over here. How many electrons do we have in the first energy level? How many places? We've got two elements, 1 and 2. Guess what? We have 2 electrons that can go in the first orbital. Then we go to the second level. What are the first electrons to be placed? The 2 in the 2s orbital. That's lithium and beryllium, right? Then what electrons get placed? The 2p orbitals. Guess what? 2, oh, there are no d's. There's the p's. P1, P2, P3, P4, P5, P6. What comes next? 3, third energy level. S1, S2. What comes next? 3, P1, P2, P3, P4, P5, P6. What comes next? Fourth energy level. S1, S2. Now we've got D's. The first time we hit a D is when we are in the fourth, after we fill 4s. Let's go back for a minute. After we fill 4s, then we fill the 3D. Here's the deal. When you get to the D's, you've got to subtract 1 from the energy level. Okay? So it's 4s1, 4s2. It looks like 4D, but it's 3D. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then goes back to 4, P1, P2. See that? After the D, goes back to 4, P1, P2. All the way across. Guess what happens? Start back over here again. 5s1, 5s2, 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Back to 5p1, 2, 3, 4, 5, 6, and so on. So you can figure out what the electron configuration should look like for any element simply by charting it out by following across the periodic table, which will be the same as drawing that slant diagram and counting them up on the slant. Now, again, that seems maybe a little bit difficult to understand. Let's go back to this. And if I were to say to you, okay, what is the electron configuration for hydrogen? Hydrogen is the most basic element, right? Look over at the periodic table. Hydrogen has an atomic number of 1. We have to count for 1 electron. Looking at the slant diagram, 1s1. That's it. That's a whole electron configuration. It's 1s1. Remember, 1s2 represents it can hold up to 2. What's the actual highest? 1s1, because it only has 1. What about helium? Well, helium is atomic number 2. I need to place 2 electrons. 1s2, both of them. That's 1 and 2. 1s2. If I go over to lithium, it's 3. 1s2, that's 2. 2s1. That's my 3. See? Remember, the superscript means how many electrons am I going to put into that orbital. So if I need to place 3 of them, it's 1s2, 2s1. That counts for all 3 of my electrons. Neon. It's over there at 10, right? How am I going to place my 10? 2, 4, 10. My electron configuration would be 1s2, 2s2, 2p6. If I look at it this way, what would it look like? 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 2p6. So the rows that represent the energy levels, the columns, the regions tell you what orbital is being filled. There's the s block, the p block, the d block, and the f block. And the particular column it's in tells you which is the highest electron in that orbital. So if I look over here and I go to, all right, chromium. I know that its highest electron, the last electron to be placed, is going to be in the energy level's 4, but it's in a D, so it's a 3D, 1, 2, 3, 4, 3D4. If I count it up, I know that it's a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4 configuration. Just by following across 1, 2, 3, 4, just writing it down in order. And if you did it by the slant diagram, it'd be the same thing. 2, 2, 6, 2, and so on. Okay? So, for example, write the electron configuration of a carbon atom. That's the question. What is the electron configuration of a carbon atom? First thing we're going to do is try to figure out how many electrons we need to place. Looking over there on the periodic table, we see carbon, and it has an atomic number of what? 6. So I need to place 6 electrons. How am I going to place those 6 electrons? What addresses are they going to fill? Okay? So I'm going to place, I'm going to just count it up, right? Let's go over to periodic table. I've got 1s2, that's 2 of my electrons. 2s2, that's 4 electrons. 2p, what? It's got to be 6 all together. I've already placed 4. What's 6 minus 4? 2. So it's 1s2, 2s2, 2p2. That 2, 4, 6 electrons are accounted for. Okay? We'll pick it up there tomorrow. The remainder of the module homework is due for Thursday.